Fine. Let's start. Number 10. The interface theory of reality. Look at the screen in front of you right now. Somewhere on it there's a little folder icon, blue, rectangular, sitting on a flat-colored background. And you know, without thinking about it, that the file inside that folder is not actually a tiny blue rectangle. There's no little blue square living inside your computer. The icon is a lie. A useful lie. It hides a storm of voltages and magnetic patterns you could never consciously manage, and it gives you instead something you can grab. Now here's the question a cognitive scientist named Donald Hoffman, professor emeritus at the University of California, Irvine, has spent his career asking, what if everything you see works exactly like that icon? Not just your computer screen, everything. The tree outside, the coffee cup, your own hands. What if space and time and physical objects are the icons, and reality, the real thing underneath, is something you have never once glimpsed? This is the interface theory of perception. And the argument behind it is not mystical. It's evolutionary. We tend to assume that natural selection shaped our senses to show us the truth, because surely an animal that sees the world accurately survives better than one that doesn't. It feels obvious. Hoffman decided to actually test that assumption, running evolutionary game theory simulations. Organisms competing over generations. Some of them tuned to perceive the truth of their environment. Others tuned only to perceive what helps them survive. Fitness, not fact. And the result was the opposite of what you'd expect. The organisms that saw reality as it truly is went extinct. Every time. They got outcompeted by the ones that saw a simplified, useful fiction. Because seeing truth costs time and energy, and evolution doesn't reward truth. It rewards grandchildren. So Hoffman's conclusion is brutal in its simplicity. Accuracy is a survival disadvantage. We were not built to see reality. We were built to see a dashboard, a heads-up display, tuned over millions of years to keep us alive long enough to reproduce. The colors, the solidity, the 3 dimensions you're so sure of, these are the icons. And like the blue folder, they're not telling you what's really there. They're hiding it so you can function. He goes one step further into something called conscious realism, where the fundamental layer of reality isn't matter at all, but networks of conscious agents, and space-time is just the headset they're wearing. That part is far more speculative, and plenty of scientists push back hard. They argue that fitness ultimately has to track something real, so perception can't be completely unhooked from reality. It's a serious objection, but you don't have to swallow the whole thing to feel the floor tilt. Just sit with the smaller claim that the world in front of your eyes is a user interface, that you have spent your entire life clicking icons and calling it reality, and the desktop never once showed you the machine. Number 9. Reality is a controlled hallucination. Let's say you accept, even a little, that perception might be an interface. The natural next question is, okay, who's drawing it? And the answer, according to a neuroscientist named Anil Seth at the University of Sussex, is sitting inside your skull right now, in the dark, having never seen the world directly even once. Think about your brain for a second. It's locked inside a bony box. No light gets in. No sound. It has never touched a single object. All it ever receives are electrical signals, blips coming down nerves, and from those blips it has to build the entire rich world you experience. The blue of the sky, the weight of your phone, the face of someone you love. None of that comes in through the senses. The senses send raw, ambiguous, flickering data. The richness is manufactured. So how does the brain do it? Seth's answer is that the brain is a prediction machine. It is constantly generating its best guess about what's out there, projecting that guess outward, and then using the incoming sensory signals only to check and correct the guess. You are not seeing the world. You are seeing your brain's prediction of the world, lightly edited by reality. Perception flows from the inside out, not the outside in. And that's why Seth calls it a controlled hallucination. Because the process that builds your normal, stable, ordinary experience of sitting in a room is the same process that builds a hallucination. Exactly the same machinery. The only difference, the entire difference, is how tightly the world is allowed to correct the guess. When the correction is strong, we call it perception. When the guess runs loose, unchecked, we call it a dream, or a vision, or a hallucination. There's no separate hallucination department in the brain. It's one system, dialed to different settings. There's a line of his that lands harder the longer you think about it. When we agree about our hallucinations, we call that reality. That's it. That's what shared reality is in this picture. Not a window we all look through. A guess we all happen to be making at the same time. Now Seth is careful, and we should be too. He is not saying the world doesn't exist. The world is absolutely real. The chair will stop you if you walk into it. What he's saying is that your access to that world is never direct. It is always a construction. The color isn't out there. Color is something your brain paints onto certain wavelengths. Solidity is a feeling your brain assigns. Even the sense that there's a single, continuous you sitting behind your eyes watching it all, that's part of the controlled hallucination too. So the strangeness of this video doesn't start out at the edge of the universe, in some exotic experiment. It starts about 3 centimeters behind your eyes. Before any physics, before any equations, the reality you are experiencing this very moment is already a story your brain is telling itself in the dark, and it has never once stepped outside to check. Number 8, quantum Darwinism. So far we've been talking about the mind. Let's go the other direction now, down into the physics, and ask a question that sounds almost too simple. Why is the world solid? Because here's the problem. Everything you see is made of quantum stuff, and quantum stuff is famously not solid. It's fuzzy. A particle doesn't have a single definite position until you look. It exists in a smear of possibilities, here and there and everywhere in between, all at once. That's not philosophy. That's just how the math of quantum mechanics works, and it's been confirmed 10,000 times over. So if the bricks are blurry, why is the building sharp? Why does the table have one location? Why does the world commit to being something instead of staying a haze of maybes? A physicist named Wojciech Zurek at Los Alamos National Laboratory has spent decades on this, and his answer has a name that tells you everything. Quantum Darwinism. Survival of the fittest for reality itself. Here's the idea. A quantum object is never truly alone. It's constantly being bumped, touched, measured by its environment. Photons of light bounce off it. Air molecules collide with it. And every one of those interactions is, in effect, the environment asking the object a question and walking away with a copy of the answer. Now, most of the object's fuzzy quantum possibilities are fragile. They get scrambled and erased almost instantly by all this contact. But a few special states are robust. They survive the bombardment. Zurek calls them pointer states, and the survival process he calls einselection, environment-induced selection. And then comes the crucial move. Those few surviving states don't just persist. They get copied, over and over, redundantly, into the environment. Think about how you're seeing anything at all right now. Light is hitting an object, and millions of photons are carrying away identical copies of where that object is, in every direction, into every eye and camera that happens to be pointed its way. The object's location is stamped onto the universe millions of times over. And that, Zurek says, is what objectivity actually is. Something is real, classically, solidly real, when the universe has made so many redundant copies of it that any number of independent observers can check, separately, and all get the same answer. Reality is the information fit enough to be broadcast. Sit with what that implies. The solidity of the world isn't a fundamental property baked into things. It's an achievement. It's the visible residue of a selection process, the handful of quantum states that won the fight to be copied, while everything else got erased. The chair is real because the universe printed 1 billion identical receipts of it. And here's the chill at the bottom of it. Most of a quantum system's information is never broadcast at all. It stays private, hidden, unselected. We only ever encounter the tiny, redundant, copied fraction, the part the environment chose to advertise. And we take that sliver, that loud surviving minority, and we call it the whole world. This one, unlike some on this list, is fairly mainstream. It's been tested in labs. But mainstream doesn't make it comfortable, because it means the firm, dependable, classical world you live in is not the foundation. It's the part that survived. Number 7. Cubism. Let's stay in the quantum world, but now let's pick on the single most important object in all of quantum physics. The wave function. It's the thing physicists write down to describe a quantum system. It tells you the probabilities, where a particle might be, what it might do. For 100 years, the deepest argument in physics has been about one question. Is the wave function a real thing out there in the world, or is it something else? Cubism, which stands for quantum Bayesianism, gives an answer that quietly detonates the whole picture. The wave function is not out there at all. It's in you. It is your personal degree of belief about what you're about to experience. This view was built in the early 2000s by Christopher Fuchs, Carlton Caves, and Rudiger Schack, and it borrows from Bayesian probability, the mathematics of how a rational mind should update its beliefs when new evidence comes in. In cubism, the wave function is exactly that, a bookkeeping device for one observer's expectations. It doesn't describe the electron. It describes what you, the agent, think the electron will do to you when you interact with it. And this dissolves one of the great horrors of quantum mechanics, the collapse of the wave function. You've probably heard about it, this spooky instantaneous moment when a particle stops being a haze of possibilities and snaps into one definite outcome the moment it's measured. Physicists have tied themselves in knots over what physically causes that collapse. Cubism just shrugs. There is no physical collapse, because there was never a physical wave to collapse. When you make a measurement and update your wave function, that's not the universe rearranging itself. That's just you, learning something, and revising your beliefs. The way your odds change the instant a card is flipped over. Clean, right? Except follow it where it leads. If the quantum state is personal, yours, then my quantum state is mine. We can each carry our own wave function for the same particle, and they can be different, and neither of us is wrong, because the wave function was never a fact about the world. It was always a fact about a knower, which raises the question that makes physicists go pale. Is there a single, shared, observer-independent reality underneath quantum mechanics at all? Or does each conscious agent move through their own private version of it, stitched together from their own experiences? Cubism doesn't force the nihilistic answer, but it leaves the door wide open, and the draft coming through that door is cold. Critics hate this. They say it flirts with solipsism, that it abandons the entire point of science, which is to describe a world that's out there whether anyone's looking or not. The cubists answer that they're just being honest, that quantum mechanics has been screaming at us for a century that the observer cannot be removed from the picture, and everyone else has been plugging their ears. You measure the particle. It gives you an answer. And cubism says that answer was never sitting out there, waiting for you. It came into being in the meeting between you and a world that doesn't fully exist until you ask. Number 6, it from bit. Now, I want to introduce you to a man because this next idea is easy to wave away as the daydream of a mystic until you find out who said it. His name was John Archibald Wheeler, and he was not a fringe figure. He was one of the towering physicists of the 20th century. He worked on the bomb. He mentored Richard Feynman. He taught Kip Thorne, who later won a Nobel Prize. He gave the black hole its name. He coined the word wormhole. When this man said something about the deep nature of reality, the entire field leaned in. And late in his life, after decades at the absolute frontier of physics, Wheeler landed on a conclusion he summed up in 3 words. It from bit. Here's what he meant. It is any physical thing. A particle, a field, a planet, space-time itself, and the bit is information, the most basic unit there is, a single yes or no, a 1 or a 0. Wheeler's claim was that the its come from the bits, that every particle, every force, every grain of the space-time continuum derives its function, its meaning, its very existence from answers to yes or no questions. That at the bottom of reality, underneath the matter and the energy, there is information, and the matter is what the information looks like from the inside. He presented it first at a conference at the Santa Fe Institute in the spring of 1989, then wrote it up in a paper with a title that sounds like a manifesto: Information, Physics, Quantum, The Search for Links. And the picture it paints turns the whole materialist story upside down. We tend to think information is something we extract from a pre-existing physical world. You measure the rock. You get data about the rock. Wheeler says no, you've got it backwards. The rock is the data. The physical world is the readout. Reality is made of answers. And tied to this is his idea of a participatory universe, which is even stranger. Wheeler thought observation didn't just reveal reality. He thought it helped bring reality into being. That the universe is a kind of vast question and answer process, and observers, by asking questions, by making measurements, are part of how it gets made. The cosmos as a participatory phenomenon, where the act of looking is woven into the act of existing. Now, to be fair, it from bit is more of a guiding vision than a finished, testable theory. Critics point out an obvious snag. Information about what exactly, if not about pre-existing things? It risks chasing its own tail. Wheeler knew it was unfinished. He called these ideas his life's final question, not his final answer. But the vision lit a fire. The entire field of quantum information science, quantum computing, the deep links between physics and computation, much of it grew in soil Wheeler turned over. Modern physicists increasingly talk about reality in the language of information, of bits and entanglement and code, and a lot of them trace that instinct straight back to this one stubborn old man. The man who named the black hole, telling us that underneath everything solid, everything heavy, everything you can kick, there is nothing but answers to questions. It from bit. Number 5. The universe is not locally real. Everything so far has been an interpretation, a way of reading the evidence. So let me give you something harder. Something that isn't a theory anyone can dismiss as philosophy. Something with a Nobel Prize bolted to it. In 2022, the Nobel Prize in Physics went to 3 men: John Clauser, Alain Aspect, and Anton Zeilinger. And the discovery they were honored for can be stated in one sentence that should stop you cold. The universe is not locally real. You have to unpack those 2 words, because each one is a pillar of common sense, and the experiments knocked both of them down. Real means that objects have definite properties, whether or not anyone is looking. The moon is there when you're not watching. Local means that nothing can influence anything else faster than light, that things are only affected by their immediate surroundings, no instant action across a distance. Real and local. Two assumptions so obvious they barely feel like assumptions. They feel like sanity. The story goes back to Albert Einstein, and this is the part that's almost too poetic to be true. In 1935, Einstein, with Podolsky and Rosen, described quantum entanglement. Two particles linked so that measuring one instantly tells you about the other, no matter how far apart they are. And Einstein hated it. He called it spooky action at a distance, and he used it as a weapon. His whole point was, look how absurd quantum mechanics is. It predicts this ridiculous, spooky link. Therefore, the theory must be incomplete. Therefore, there must be hidden information, hidden variables, carried inside the particles all along, and reality is local and real after all. He was trying to rescue common sense. For decades, it looked like an unanswerable philosophical standoff. Then, in 1964, an Irishman named John Stuart Bell did something miraculous. He found a way to turn the argument into a number. He proved that if the world really is local and real, with hidden variables, then certain experimental results can only add up so high. There's a ceiling, a limit. But if quantum mechanics is right, the results sail straight past that ceiling. Two different worldviews, and a measurable line between them. So, they did the experiment. Clauser ran the first versions in the early 1970s. Aspect tightened it in the early 80s, switching the detectors in billionths of a second after the particles were already in flight so they couldn't conspire. Zeilinger sealed the last loopholes, even using the light of distant stars and quasars to choose the detector settings. So the choice was made by photons that left their sources billions of years ago. And every time, every single time, the universe blew straight through Bell's ceiling. Einstein was wrong, not a little wrong. Wrong about the deepest thing. The particles do not carry definite, pre-existing properties. The spooky link is real. You cannot keep both locality and realism. At least one of them has to go. Let that settle. The thought experiment Einstein designed to prove reality was solid, and local became the exact tool that proved it isn't. He set the trap for quantum mechanics, and the universe used it to catch him. Now, the careful caveat. Because it matters. Not locally real does not mean nothing exists, and it does not mean magic. The world is still stable. Physics still works flawlessly. What the result does is forbid a certain comfortable story, the story where every object quietly carries all its properties around with it, fully formed, whether you look or not. That story is dead. The Nobel Committee signed the death certificate. The moon may be there when you're not looking, but the particles that make it up are playing a game far stranger than just sitting there, being real. Number 4. The universe is a computation. Now, you've probably heard the simulation hypothesis. The idea that we're living inside some advanced civilization's computer program, that there's a machine somewhere, and a someone who built it, running us. That's a fun idea. This is not that idea. This one is stranger, and in a way, more serious, because it doesn't need a someone at all. The claim here is not that the universe is being run on a computer. The claim is that the universe is the computation. That reality, at its very bottom, is not made of particles, or fields, or strings, but of information being processed, step by step, according to simple rules, with no programmer and no machine outside it. The cosmos isn't in a computer. The cosmos is the computer, and the program, and the output, all at once. This is an old and stubborn idea, and it comes from serious people. Back in 1969, a German engineer named Konrad Zuse, who built some of the first programmable computers in history, wrote a book called Rechnender Raum, Calculating Space. And in it he proposed something audacious, that the physical behavior of the entire universe is being computed on a basic level by the universe itself, like a vast cellular automaton. A cellular automaton, if you've never met one, is one of the most beautiful ideas in all of science. Picture an enormous grid of cells, each one either on or off. Now give it one simple rule. A rule about how each cell should change based on its neighbors. Apply the rule everywhere, all at once. That's one tick of time. Then do it again and again. And here's the miracle, that from absurdly simple rules, repeated, you can get staggering complexity. Patterns that move, that grow, that collide, that compute. Whole little universes of behavior unfolding out of almost nothing. Zeus's question was, what if that's literally what we are? What if space is a grid, time is the ticking of the update, and everything, you, the stars, this moment, is just the pattern the rules are currently drawing? The torch was carried forward by Edward Fredkin, who championed digital physics, and decades later by Stephen Wolfram, who launched a major project in 2020 to find the actual rule, modeling the universe as an evolving network that rewrites itself. And by Gerard de 't Hooft, a Nobel laureate no less, who argues that underneath quantum mechanics, there may be a deterministic cellular automaton grinding away. And here's the part that should make you tilt your head. If this is true, then space and time are not smooth. They're pixelated. There's a smallest possible step, a grid too fine for any instrument to resolve, and the seamless, flowing, continuous reality you feel yourself gliding through. The unbroken sweep of a moment is an illusion, a very, very high-resolution illusion, generated by a grid clicking through states one frame at a time. Like a film that looks like motion, but is really just still pictures. Fast. Now, in fairness, no one has found the rule. Not Zusi, not Wolfram, not anyone. Critics say the project overpromises and hasn't outpredicted ordinary physics yet, and that making a fixed grid agree with Einstein's relativity is brutally hard. It's a research program, not a victory. Fair, but strip all that away and the bare possibility remains, standing there, refusing to leave. That the universe might not be a thing that contains computation. It might be a computation that contains you. Number 3, superdeterminism. I want to come back to those Bell experiments from a few minutes ago. The ones that proved the universe isn't locally real, because there is a way out. There is exactly one loophole that can save the old, comfortable picture of a local, definite reality. And it is so disturbing that most physicists would genuinely rather accept spooky action at a distance than take it seriously. It's called superdeterminism. And to understand it, you have to look closely at a hidden assumption buried inside every Bell experiment ever done. When the scientist chooses which way to orient the detector, we assume that choice is free, independent. That what the experimenter decides to measure has nothing to do with what the particle was secretly up to. That assumption even has a name, the freedom of choice, and it feels unbreakable. Of course, your choice is independent of the particle. How could it not be? Superdeterminism says, what if it's not? What if the setting of the detector and the property of the particle are not independent at all, but were both fixed in advance, correlated by the initial conditions of the universe itself, all the way back at the Big Bang? If that's true, the whole spooky mystery evaporates. The particles don't need to communicate faster than light, and they can have definite properties all along, because the experiment was never a fair test. The universe rigged the match before it started, quietly arranging it so that whatever you chose to measure always lined up with what the particle was already going to be. No spookiness required, just a cosmos that was choreographed from the first instant. You see immediately what it costs. It costs your free will. Completely. Because if the universe is arranging the experimenter's choices to match the particles, then the experimenter isn't really choosing. And if that's true for the scientist in the lab, it's true for you, everywhere, always. Every decision you've ever made, every word in this sentence as you hear it, every thought you're about to have, all of it fixed, locked in, written into the initial conditions of reality, 14 billion years ago. Not just determined, choreographed down to the firing of a single neuron so that the grand quantum books always balance. And this isn't a crank position. Gerard 't Hooft, the same Nobel laureate, has developed it seriously. His cellular automaton interpretation of quantum mechanics leans on exactly this kind of determinism. The physicist Sabine Hossenfelder has argued, in papers and on her blog, that superdeterminism is the forgotten solution, that the field dismissed it too fast out of discomfort rather than evidence. Because here's the truly maddening part. This loophole cannot be closed. Ever. Every other loophole in the Bell experiments, the physicists sealed them, one by one, with cleverer and cleverer setups. But you cannot seal this one, because any source of randomness you bring in to make a free, independent choice, a dice roll, a quantum number generator, the light of an ancient quasar, could itself have been predetermined, correlated, part of the same cosmic script. There is no choice you can make to prove your choices are free, because the proof itself could be rigged. It is untestable by its very nature, which is why most physicists set it aside. Not because they've disproven it. They can't. But because a theory you can never test feels like a dead end. And quietly, because the alternative is unbearable. So you can keep your local, real, sensible universe. You just have to accept that you were never free inside it. Not for 1 second. Number 2, ER equals EPR. Of everything on this list, space itself has stayed safe. We've questioned your perceptions, your free will, the solidity of matter, even whether there's one shared reality. But space, the simple stage, the empty room the universe happens in, the distance between you and the wall, that has felt like bedrock. This next idea comes for the bedrock. In 2013, two of the most respected physicists alive, Juan Maldacena at the Institute for Advanced Study and Leonard Susskind at Stanford, proposed something so strange it took the field years to even know how to argue about it. They wrote it as an equation made of letters. ER equals EPR. Let me decode that because it's gorgeous. EPR is entanglement. The Einstein, Podolsky, Rosen pair, those two linked particles from earlier that share a fate across any distance. ER is the Einstein, Rosen bridge, which is the technical name for a wormhole, a tunnel through the fabric of space-time connecting two far-apart places. For decades, these were considered completely unrelated. One was a quantum oddity about information. The other was a science fiction shortcut from general relativity. Different fields, different math, strangers. Maldacena and Susskind said, what if they're the same thing? What if two entangled particles are connected by a tiny, tiny wormhole? That the spooky link Einstein hated isn't a signal racing across the gap between the particles, but a bridge joining them behind the gap, through a hidden geometry, so that in some deep sense they were never really apart at all. And if you let that thought grow, it becomes one of the most radical ideas in modern physics. Because then entanglement isn't something that happens inside space. Entanglement is what builds space. The threads of quantum entanglement, woven densely enough, are what stitch neighboring regions of reality together into the smooth, connected space-time we live in. Space is not the empty stage. Space is the fabric, and entanglement is the thread. There's a thought experiment that makes it vivid, and it's chilling. Take two regions of space, side by side, connected, ordinary. Now, imagine slowly removing the entanglement between them, snipping the quantum threads one by one. According to this picture, as you do that, The two regions don't just lose some abstract correlation, the space between them comes apart. The distance stretches, tears, and the regions fall out of contact entirely, as if the geometry itself were unraveling. Pull out enough thread, and there is no more between. Space is sewn, and you can unstitch it. This reframes that old spooky action at a distance in the most beautiful way. The particles seem to communicate instantly across a vast distance, faster than light, impossibly. But ER equals EPR whispers. There is no distance. Not down where it counts. The two particles are joined by a private bridge that doesn't go through the space between them. The gap you see is the illusion. The connection is the truth. I'll be honest with you, the way I try to be. This is still a conjecture. It is not proven. It's a deep, suggestive hint, supported by some gorgeous mathematics and a few daring experiments on quantum processors, and it might yet turn out to be wrong, or only part of the story. Physicists are still fighting about it. But hold the picture in your mind anyway. The space around you, the room, the air, the reach between your hand and this screen may not be a fundamental thing at all. It may be a tapestry, held together by countless invisible quantum threads, and the universe, it seems, knows how to pull them out. Number 1, space-time is doomed. We've spent this whole journey chipping away at reality. Your senses, an interface, your perceptions, a controlled hallucination. The solid world, a broadcast of survivors. The quantum state, a personal belief. Matter, made of information. Local realism, dead by Nobel decree. Continuity, possibly pixels. Free will, possibly scripted. And space itself, possibly woven from entanglement and able to be unstitched. So what's left? What's the last thing standing? It's the stage. Space-time. The deepest, most foundational thing in all of physics. The arena that every event, every particle, every moment plays out within. Surely that, at least, is the floor. The thing the rest is built on. There is a physicist named Nima Arkani Hamed at the Institute for Advanced Study, widely considered one of the sharpest minds in the field, and he has a phrase he repeats in lectures, almost like a warning. Space-time is doomed. Not space-time is mysterious. Not space-time is curved. Doomed. He believes that space and time are not fundamental at all, that they are emergent, an approximation, an output of something deeper, and that physics is on the verge of having to leave them behind. And he and a colleague, Jaroslav Trunka, found something in 2013 that makes the warning concrete. It's called the amplituhedron. Here's the setup. When physicists want to predict what happens when particles collide, the standard method is monstrous. You draw diagrams, Feynman diagrams, one for every possible way the collision could unfold. And for complex interactions, there can be thousands of them, hundreds of pages of grinding calculation, all built on the assumptions of space, time, and locality. The rule that things only affect their immediate neighbors. Arkani Hamed and Trunka discovered that for certain interactions, you can throw all of that away. All of it. And instead, you can compute the answer by finding the volume of a single geometric shape. A multidimensional jewel. The amplituhedron. One object. One volume. And out comes the answer that took thousands of diagrams to reach. Now here's the part that breaks your brain. The right way. That jewel does not live inside space and time. It has no reference to them at all. There's no when in it, no where, no sequence of events, no locality. It is a timeless, spaceless, geometric object sitting outside the arena entirely, and it gives the correct answer for events we thought happened inside the arena. Space and time aren't inputs to the calculation. They fall out of it. They emerge at the end as a kind of shadow the geometry casts. Think about what that suggests. We have always assumed that space and time are the ground floor of reality, and that the deep laws of physics must be written in their language. The amplitude-hedron hints that it's the other way around, that underneath, reality is geometry, pure relationship, with no space and no time anywhere in it. And that space-time, the thing you are absolutely certain you are sitting inside of right now, is not the foundation. It's the output, the rendered surface, the shadow of something that doesn't live in space or time at all. I'll give you the honest caveat one last time, because you deserve it. The amplitude-hedron, as it stands, works for a specific, idealized, simplified theory, not yet for the full messy universe. No one is claiming the chair under you is fake. What they're claiming is deeper and quieter. That when we finally find the bottom of physics, space and time will not be there. There'll be things that appear, like temperature appears out of moving atoms, real as an experience, but not fundamental as a thing. And that's where we end, with the strangest thought of all. For your entire life, you have believed you live somewhere, and somewhen, a place and a time. That has felt like the one thing nobody could ever take from you. And the deepest mathematics we have is gently, patiently suggesting that the place and the time were never the real story. That you and everything you have ever loved are a pattern being cast by a geometry that exists nowhere and never. The universe you live in may not be unreal, but it may not be the bottom. And the bottom, it turns out, has no room in it for you, or for space, or for a single passing second. It just is. Outside all of it, quietly holding everything up. Thank you for watching and sticking till the end. We've got plenty more videos coming in the future. Hit that subscribe button so you don't miss them. See you in the next one.